Hello again, welcome back. The next lecture in the sequence is one on Opaite Analgesia. This follows on from the lecture we had a short while back when we looked at the pain pathways. And in that lecture, if you remember, we talked about the intrinsic analgesic system. So just to take you back through the pain pathways as a little bit of a precursor. If you remember, we said you had the nociceptors, which are the thermal nociceptors, the mechanical nociceptors, and the polymodal nociceptors. And they're the naked nerve endings that respond to the various stimuli. They then cause the firing of action potentials up through the afferent pain fibres. And those pain fibres can either be A delta fibres, which are large diameter myelinated ones, and they carry the fast pain signals. Then you've also got the C fibres, which are the small diameter, unmyelinated ones, and they carry the slow pain signals. Once they get to the spinal cord, they release substance P as the neurotransmitter, which activates the spinothalamic tract, with branches off to the reticular formation, hypothalamus, limbic system, and somatosensory cortex. And that gives you the 5 aspects of pain: perception of pain, localization of pain, increased alertness to pain, the behavioural response, and the emotional response that you perceive. And if you remember, we said that as well as the reticular formation firing up the way, there are also descending pathways coming down, which release endogenous opiates, which are the endorphins and the enkephalins, onto opiate receptors situated here on the presynaptic membrane that block the release of substance P. And as a result, they block the pain signals. And that's just a little bit of text there, which is talking about that descending pathway blocking the release of substance P. Therefore, if that happens, you don't get the stimulation of the pathway, the spinal thalamic tract. And again, little diagram just to remind you. This is exactly the same diagram as was in the pain pathways lecture, where we see the reticular formation firing down as well as firing up, firing down, releasing the endogenous opiates, opiate receptors, blocking the release of substance P, blocking the spinothalamic firing. Now that built-in analgesic system, the endogenous opiates, that consists of the endorphins, the enkephalins, and dynorphin. Now, they are analgesic neurotransmitters, which are released from that descending pathway, and they bind with the opiate receptors on the afferent pain fibre terminal at the level of the spinal cord. And so therefore, as we mentioned before, suppress substance P release and block transmission of the signal. The very fact that we do have these opiate receptors then gives us a pharmacological target to produce a range of analgesic agents that would be classed or considered exogenous opiates, as opposed to the endogenous opiates we see over here. Now, thinking about analgesia, thinking back to the pain pathways, there are 3 main ways that we can get a level of analgesia. 4 if you count the general anaesthetic. But taking general anaesthetic as a separate entity, we can then deal with the opioid analgesics, which is what we're going to discuss today, which are acting on that endogenous pain system. The non-steroidal anti-inflammatory drugs, which we're going to come back to, and the local anaesthetics, which I believe you've also seen the PowerPoint for. The local anaesthetics are fairly straightforward. They simply block sodium channels, therefore they block the depolarization phase of the action potential. And if you don't get the rising phase of the action potential, you don't get the falling phase of the action potential. Therefore, you don't get the action potential. So therefore, the signals are not processed and firing from the site of the damage or the site of the painful stimuli. But as I say, for the purposes of this lecture, we're focusing here. Now, there are 2 main classifications of drugs that act on the opiate receptors. We have the opiates themselves, which are analogues of morphine, and then we have the synthetic derivatives, which are structurally unrelated to morphine. So basically, morphine-like and morphine-unlike, if you want to put it as simple as that. Now, morphine and the related analgesics, that are the opiates, they're going to act on the opiate receptors. Now, there are three major classes of opiate receptor identified in the human body: mu, kappa, and delta. Each one has a very distinctive profile in terms of where you find it. The ones that we're interested in for mediating the analgesic action are the mu receptors. But the others can have a potential role in the process of analgesia. Now, as we said, in order to get the analgesia, you have to inhibit the release of the mediators from that pathway, the main one being substance P. But glutamate and nitric oxide also have a part to play. We don't have enough time to go into the detail of that at the moment, but glutamate is a major excitatory transmitter, and therefore it's going to stimulate firing of neurons. So therefore you can kind of see where that's coming from. Now, the other thing we've got to remember is that it's the activation of the mu receptor that gives you the analgesia, but if a drug also works on the kappa receptor, that will antagonise analgesia. So you've got to be very careful if the drugs that you're giving are not specific enough. You need a mu agonistic action, but if you also have a kappa agonistic action, that will reduce the analgesia. So you don't want that happening. But this explains why buprenorphine is quite an effective agent. Buprenorphine is a partial mu agonist. So it's not as good on the mu action as morphine, but it's a kappa receptor antagonist. Now that means that you're blocking this response, therefore you're blocking the antagonism of the analgesia, so you're actually enhancing the analgesia. So therefore, what buprenorphine does is, it might not have as good an analgesic action in terms of just thinking of the mu receptor, but the kappa antagonism, it can actually, if you like, amplify its own action. It can enhance its own effect. So that combination of mu agonist, kappa antagonist is quite an effective combination. Now, different opiates will have different selectivity in terms of the receptors that they actually work on. So again, we've already said that we have the mu receptors, we have the kappa receptors, and we have the delta receptors. And each opiate has a selectivity profile. And they can be, and you can call them or refer to them as they're either agonist, partial agonist, or antagonist. And if you can't remember that terminology, I refer you back to the very early lectures where we explained what agonist, partial agonist, and antagonist actually means. The way that they're classified then is by the way that they act at the opioid receptors. So, the full agonists, as they're called, they act principally at the mu receptor. That's morphine, diamorphine. Now, diamorphine is heroin. Then we've got pethidine, codeine, and dextropropoxyphene. Now, they are all full agonists, and they have a very weak agonistic activity at the delta and the kappa. So, although that agonist activity at the kappa has the potential to reduce their effectiveness, because it's a weak agonist, it doesn't reduce it that much. We then get drugs that are mixed agonist-antagonist. Now, we've already mentioned, the buprenorphine. It's actually a mixed partial agonist-antagonist, and so it enhances its own activity. But there are others that have agonistic actions at kappa, but weak mu. Now, these kind of drugs are not necessarily going to have any clinical effectiveness, because for analgesia, you don't want mu antagonism, you want mu agonism. So therefore, why we got a lot of these drugs are used simply as a way, they're like pharmacological manipulators. They're a way of manipulating the system to get a better understanding of what the receptors are actually doing. So they might not have a clinical perspective, but they are a research tool. But the ones we're really interested in are the full agonists like morphine and diamorphine, and the mixed partial agonist antagonists like buprenorphine. Now, if you look at the British National Formulary, you will see the drugs listed: morphine, buprenorphine, codeine, diamorphine, which is heroin, and dihydrocodeine. This is the interesting one, diamorphine, because people often are concerned that that are, themselves or a relative or family member, friend, whatever, is receiving heroin, and they're worried about addiction. But actually, there is evidence to support the fact that it's not necessarily the case that a person taking heroin for analgesia, for a chronic illness, would develop a sort of dependency on the drug. The evidence would suggest otherwise. So as I say, what they're doing is they're acting on the receptor as an agonist, and that blocks the release of substance P, so therefore you don't get the firing of the spinal thalamic tract. And therefore they have both antinociceptive, which is actually the blocking of the pain pathway, and analgesic, which is the fact that because they're blocking that ascending pathway, they're also taking away the other aspects of the pain, such as the unpleasantness, etc. Now, as we said, most of the ones we've mentioned that are kind of prescribed, your ones like morphine, heroin, dihydrocodeine, etc., they're working on the mu receptor. So you get the analgesia, you get the antinociception, but what you also get with them is you get a euphoria, and well, this is one that you've got to be careful of. You can get a respiratory depression. Now, that's because there are mu receptors in the brainstem, in the respiratory control centres, and when the opiates act on those receptors in the brainstem, they reduce the ability of the brainstem to respond to CO2. Now, CO2 is the driving force that makes us breathe. So as the CO2 levels rise, our respiratory rate goes up to clear that CO2. If the cells within the brainstem are less responsive to that CO2, the CO2 levels will rise, but the respiratory system won't necessarily kick in to overcome that and clear it away. So you actually can get a respiratory depression. Now, that has potential to be quite serious. I'll give you a case in point. I don't often use case studies, but I'll give you a very personal case study of my own father. My own father suffered from significant respiratory conditions. He died a number of years ago now, but he suffered quite badly from emphysema, bronchiectasis, etc., etc. And what happened was, because he was having such a poor respiratory health, they gave him steroids to try and reduce the inflammation. Now, long-term steroid use resulted in osteoporosis, and osteoporosis resulted in significant joint pain, particularly at the hips. Now, because of his respiratory condition, he wasn't hospitalised all the time, but he wasn't up and about much, and he spent a lot of time either in a chair or in a bed. And that just aggravated the pain from the osteoporosis. Normally in that situation with osteoporosis, there would have been the potential to give opiate analgesia. But in my father's case, they couldn't, because that would have depressed the respiratory system further and could actually have led to respiratory failure. So that's where these kind of things like the drug interactions and the consequences of one drug might limit you using a particular drug of choice. The other thing that happens is you get a meiotic reaction. So meiosis happens. The constriction of the pupil takes place, and that's because it stimulates the cranial nerve number 3 in fact, and you get a narrowing of the pupil. That's sometimes one of the signs. If you're ever watching the movies and they've got somebody who is high on drugs, and one of the telltale signs is that they're high on heroin is they've got pinpoint pupils, because the pupil is constricted so much because of the action of the opiate stimulating through the cranial nerve 3, causing that narrowing right the way down. You also get emesis, and that's because the opiates also stimulate the chemoreceptor trigger zone, the CTZ, which sends signals to the vomiting centre in the brain. Again, that might be something that you're already aware of. It's quite common for there to be a problem or a potential for people who are abusing opiates to actually choke on their own vomit. And that's because they take the opiate, they take the heroin, it stimulates the emetic centre, therefore it makes them sick. Now normally before we have an emetic response, the first thing we do is take a deep breath in. Now, the reason for taking the deep breath in, excuse me, the reason for taking the deep breath in is that once you've actually vomited, you can then clear the system with an outflowing of air and a cough and a splutter. And that way you reduce the risk of any of what you've vomited coming back down the airway. That can be problematic because, as we've mentioned in the earlier slide, these drugs can also depress the respiratory system. So it does happen, and you can have the potential where an individual would be sick and they wouldn't have the respiratory power to clear their airway, and that could lead to potential complications and in some cases death. So that's just something, as I say, not necessarily quite so common when someone is being medicated properly and being watched properly when they're on these medications. You can also get constipation because the opiates reduce the GI motility, gastrointestinal motility, and the individual can become constipated. And then if they get into a period of time where they're not taking the drug, they can flip from constipation to what you would term fecal urgency, and that can be quite significant and quite problematic. Now, there is this problem with tolerance. Now, tolerance means that the more you take the drug, the more you need to get the same effect. You build up a kind of resistance to it. There is also a possibility of dependence, and you've got to be careful because there could be physical dependence, the body needs it, and there could be psychological dependence. Psychological dependence is much more common in drug-seeking behaviour in an addict. Now, I mentioned it earlier that there is that thing that people might worry. What if a relative, friend, etc. is on heroin as an analgesic and they are concerned about addiction? There was a huge study done back in the 1960s, 70s with American service personnel returning from the Vietnam War. And what they found was they were turning up at the army, the services hospitals, and there were a number of people who were addicted while they were getting the treatment for whatever it was, physically that had happened to them. It was noticed that they were showing signs of addiction. And what they realised was there would be a group of people who were using opiates in Vietnam. When they came home, some continued to use and others did not. And when they investigated that further, Those that were continuing to use, in the main, had been using before they went, and those that didn't continue to use hadn't been using. So those that hadn't been using, it became apparent that they'd only been using to, if you like, deal with the horrors of what they were observing. And that sort of, situational aspect to the dependency, and or the lack of dependency, if you want to look at it that way, is what gives us that kind of sort of security that you're not going to get into a situation where everyone who takes drugs as an opiate for analgesia will become addicted to them. So, what you need to work out for today then is, for today's lecture, you need to get your head around the fact that, just refresh your memory of the pain pathway, the endogenous analgesic pathway, the role of the opiate receptors, mu, kappa and delta, and the fact that mu is the main one implicated in the analgesic and antinociceptive action of the opiates. Thank you.